Hello, algebra students. This is going to be our second lesson from our unit on quadratics. And in this lesson, we're going to be building on what we learned in the first lesson about how quadratic functions relate to geometric patterns. There is a warm-up question on the screen that will help get our conversation started today. So go ahead, pause the video, and try answering those questions now. All right, I'm going to go ahead and scroll down. It's the same warm-up question, but just a little bit larger. And the focus of this is finding area. In order to find area, we need to remember that to find area, you are multiplying the two sides of the shape. So for example, if the side length is 4 of this first one, to find the area, I just have to do 4 times 4, and that would give me 16 for the area of that shaded in blue part. Figure B, we've got the side length of that large square is still 4, but if I want the area of the blue spot, I'm going to have to find the area of the overall shape, which I know from figure A, and then take out that little white spot there. And so for figure B, I would still be doing my 4 times 4, or remember you can also write 4 squared, but then I have to subtract out the area of that white square there, which would be 1. And so that gives me 16 minus 1, and the area is 15. When it comes to this last one, there's a couple different ways you can do it. If the area of the square, if the two sides of the square are 4, that means the area of this first square here is 16. I have 2 squares though, so the area of each of those is 16. And then I still have that one little tiny one there. So that would be 1 times 1 or 1. So for the area of C, I could say I'm doing 4 times 4 plus another 4 times 4 plus my 1 there. And anytime I wrote 4 times 4, you can write 4 times 4, or you can also write 4 squared down. 4 squared would find the area of A, 4 squared minus 1 would find the area of B, and then 4 squared plus 4 squared plus 1 would find the area of C. When we go to do the second part of the question, it's asking what are all these areas if we don't know the side length? And we're going to use X to represent that. Well, I can use the math I did from the first part where I had the number and then just switch out the 4 for the X. So for this first one, if we don't know the side length, I would have to do X times X, or we could say that's the same thing as X squared. For the second one, I don't have a result from the first one to calculate, but I do know whatever that result is, I would be taking 1 from it. I would take out the area of that one small square there in white. And then for this final one, if each of these sides is X, that means the area of this first one is X squared, the area of the second one is X squared, and the area of that one is still 1 because I do have the dimensions of that one. So I could write X squared plus 1, or you can simplify that. That X squared plus X squared is 2X squared plus 1. Both of those would be correct. This relates to our conversation we had in the first lesson about geometric patterns, because we're seeing, especially here with the X, that a lot of these X squareds are coming up. And we ended that first lesson talking about if an expression or an equation has X squared in it, that makes it a quadratic expression or a quadratic equation. And so we're going to continue working on that idea today and writing some equations from these quadratic geometric patterns. The goal for this lesson is to be able to use information from a pattern of shapes to write a quadratic function in different ways. And by different ways, notice that even for some of these, there was a couple ways we could write it. You could write 4 times 4, you could write 4 squared, you could write X squared plus 1, or 2X squared plus 1. So for a lot of these, there's not only one correct way to write something to express the pattern. We are going to start with this pattern right here of expanding squares. And so the best way to check and see if you can identify a pattern is to see if you can predict what would come next. And so looking at step 1, step 2, and step 3 of this pattern, see if you can predict what step 5 and step 18 look like. You could write a description down in words. I think it's easiest to draw a picture of what step 5 and 18 would look like. And then once we predict step 5 and 18, go ahead and count how many small squares would be in step 5 and how many small squares would be in step 18. Go ahead, pause the video now and try this problem. All right. One of the strategies you can use as you're looking at these patterns is seeing if you find any connection between the step number and what you're looking at. So for example, for step 3, I noticed that in the center of this pattern, I've got a 3 by 3 square right there. And that's true for all of them. Step 2, I've got a 2 by 2 square. Step 1, I've got a 1 by 1 square. And so when we go to predict what step 5 and step 18 would look like, that pattern would continue, where step 5 would have a 5 by 5 square in the center, and step 18, it would be much larger than this, but it would have that 18 by 18 square in the center. There's one part of this picture that remains constant no matter how big the picture gets, and that's these 4 squares on the corners. Every single time we've got 4 squares, no more, no less, and they always happen to be on those corners. So for step 5, I would still see those 1, 2, 3, 4 squares, and then same thing here, those 1, 2, 3, 4 squares. When it comes to the second part of calculating how many squares are in each of these, you could definitely go, for example, for step 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 to get that step 3 has 13. But there's an easier way to calculate these, and it's by noticing how we've already broken up the picture. Every single time, I can calculate first that square in the middle that I've got in yellow. So for example, here it would be 3 by 3 or 3 times 3. And then I can add in those 4 purple ones. So 3 times 3, 9, and 9 plus 4 gets me to 13. So step 2, I would be doing the 2 times 2 to get that center part, and then plus those 4 squares, and that would give me a total of 8. Step 1, it's just a 1 by 1 square, right? But then I'm adding those 4 in purple to get 5. And so to find our total for each of these, I'm going to switch and match the colors. For step 5, I would have to do 5 times 5. I'm going to also write it as 5 squared. And then step 18 would be 18 times 18, or 18 squared. That would tell me how many are in that yellow section in the middle. And then once I get that result, I'm adding 4 to add those 4 squares on the corners. And so if we do that, 5 times 5 is 25, plus 4 gives us, there's 29 in that one. 18 times 18 is 324, and 324 plus 4 gives us 328 for that final one. Being able to look at a pattern like this and be able to identify that pattern. So identify that every single time we're getting that square in the center that's getting larger, but then those 4 on the corners are remaining consistent. That helps us with the main goal of this, which is to write an expression to represent the total number of squares. And so that's where we're going next, is here we're going to write an equation to represent the relationship between the step number, which we're going to call n, and the number of squares, which we're going to call y. If you wanted to come up with this, you can always create a table and see if you can notice that pattern. But we've kind of talked through it up here, where that pattern is every single time I'm using multiplication or an exponent of 2 to find the area of that yellow square in the middle, and then I'm adding 4 for the 4 squares on the corners. So a way to think through this is if we jump to step n, what would that picture look like? Well, for step 1, we had a 1 by 1 square in the center. Step 2, we had a 2 by 2 square. Step 3, we had a 3 by 3 square. So for step n, in the center, I would have an n by n square, and then we would still have those 4 squares on the corner. And so if I wanted to write an equation to say how many total squares there are here, Just like we were doing earlier, I would start by using multiplication to find how many squares are in this yellow area. So you could say n times n, or you could say n squared. And then we would also add these 4 squares on the corners that are in purple. And so both of those expressions would represent the total number of squares. It did say to write an equation, so I could just finish this by saying if you do n squared plus 4, that gives you the total number of squares, which we're calling y. When you write equations, you can always check your equations using some answers you are very confident about, like up here. So for example, our equation we just wrote said the number of total squares equals the step number squared plus 4. I could check that using any of these numbers here. So for example, step 5, we said the answer is 29. If I put 5 for the step number, 5 squared equals 25 plus 4, it does give me the answer it should, which is 29. If we had made a mistake somewhere in our equation, I wouldn't be getting 29 as the answer. I would be getting something else. So keep that in mind as a way you can check these. Your first attempt at writing an equation doesn't have to be perfect, but you can use that check to help you figure out what might need to change here. So in that first one, we were looking at the pattern and coming up with the equation, but we've talked a lot about this. We want to be able to go both ways. So we want to also be able to look at an equation, a quadratic equation. I know it's quadratic because it's got that n squared there. And we want to be able to come up with what a pattern might look like. In order to do this, I'm going to use what we talked about in yesterday's lesson and what we talked about in this earlier problem above here. Notice that that quadratic piece, the n squared, that matched up with this expanding square here. We had used those words expanding square in our lesson yesterday and again today, where that quadratic part, the n squared or n times n, in a pattern is going to look like a square getting bigger and bigger and bigger. A 1 by 1 square, a 2 by 2 square, a 3 by 3 square. Here we were adding 4, which meant every single picture I needed to add 4 more squares. I needed to add 4 more squares. So one of the differences in this next one is there's not addition, there's subtraction. Use the examples from yesterday and the examples today to help you try to draw a pattern for this equation here. And you're going to do the first 3 steps. So you're going to draw a picture of step 1, step 2, and step 3. If you have a hard time with step 1, skip over step 1 for then and try step 2 and step 3 first, and then you can go back and try step 1. Go ahead, pause the video, and try that now. For this pattern, in order for me to draw it, I'm going to just start by not worrying about that -1. I'm going to start with the n squared part. That's the part we've really been focusing in on in yesterday and today's lesson, and that's the part that we said looks like an expanding square. So for step 1, n squared means I would have a 1 by 1 square. For step 2, it would mean I have a 2 by 2 square. And for step 3, it looks like a 3 by 3 square. We did an equation yesterday of y equals n squared, and it looks like this. It looks like a square getting bigger and bigger. The change we need to make to this image, this pattern, is I want it to not just represent n squared, I want it to represent -1. And so that -1 is consistent. It means I'm going to be taking away 1 box every single time. So I had said if you're having a little bit of an issue with step 1, start with step 2 or step 3. I've got n squared already drawn, and I want to take away 1 box. So maybe I always take away this box over here in the top right. Doesn't matter which one you take away, but I'm going to choose that one. For step 2, I'm taking away 1 box in the same spot in the top right. And for step 1, I'm taking away 1 box. So that means my final image for these, for step 1, I would have nothing. I'm just going to write the word nothing here. For step 2, I would have 1 box missing from my 2 by 2 square. So it would look something like that. And then for step 3, it's getting a little messy. It would look, I messed up. I was trying to not draw that 1 box and I still messed up. Let's do it this way. There we go. It would look something like that, where you've got that one box missing in that top right corner there. To summarize what we're seeing here, if you're adding a number, not a variable, but a number, it looks like you're having that many extra boxes added every single time. So our +4 matched up with me adding 4 purple boxes for every single picture. And if you see subtracting a number, again, not a variable, but a number, it means you're losing that many boxes in each picture. So -1 meant I lost 1 box in every single step of my pattern. There's one final pattern we're going to look at in this lesson, and that is going to be this pattern here. Again, the best way to see if you understand the pattern is, are you able to sketch the next step? And so pause this video, look over this pattern as long as it takes, and see if you can figure out what step 4 would look like. Once you've got a picture drawn, come back to the video and see how you did. One of the strategies we've been mentioning is starting off by seeing if you see a connection between the step number and the picture. So in class, sometimes students start by noticing, okay, step 1, this is 1 square wide. Step 2, this is 2 squares wide. Step 3, this is 3 wide. And so step 4, I know, is going to be 4 wide. Here, though, I don't really see a square. These are all rectangles. And so when we look a little closer, we notice each time they're getting 1 taller. So here I'm starting with 3, and then I get to 4, and then 5. So this next one here must be 6 tall. And so it's going to look like a 4 by 6 rectangle for step 4. We could continue that pattern. Step 5 then, instead of being 4 by 6, would be 5 by 7 there, and so on. One of the questions I'm going to ask you is, a lot of times people figure out the pattern here by just looking at what came before it. So 3, 4, 5, 6, 7. I'm curious, do you know what step 100 would look like? That's really going to give you an idea if you want to understand this pattern. Well, we've said step 100. I know the 100 tells me how wide it's going to be. And then for the height, I'm going to have trouble making it this tall. We have to notice the relationship between the step number and this other side. So step 1, we were at 3. Step 2, we were at 4. Step 3, we were at 5. Step 5, we were at 7. Notice the height is always 2 more than the width. And so here, the height, do you know what the height would be? It would be 102, which this picture is definitely not showing. But there's that important idea there of not just continuing this pattern, but being able to predict a real future one that's far away from steps 4 and 5. And so that helps me identify, okay, I know the width is my step number, and then my height is just going to be 2 more than that. The next thing I want to think about then is this idea of what type of relationship we're looking at. We had said yesterday and today that any of those patterns where you see that square getting bigger and bigger were quadratics. But here we're talking about rectangles. I don't see a square for any of these. I'm looking at rectangles. So let's talk about what type of relationship this is. In number 2, we've got Kieran says that the pattern is growing linearly because the step number goes up by 1 and the number of rows and the number of columns also is going up by 1. So it keeps going up by 1, meaning it was a width of 1, then a width of 2, a width of 3. The height was 3, then 4, then 5. It just keeps going up by 1. What do you think? Is this linear? Pause the video if you need more time to think. It might be tempting to say that because we've talked a lot about how linear relationships have that constant addition or subtraction. So for example, when you're looking at a pattern where there's 2, 4, 6, 8, if you see that constant addition, that means it's a linear pattern. But here, we don't want to focus on the width and the height. We want to focus on the total number of squares. This first one here is 3. This next one here has 8. And then we've got 15. And when I look at those numbers, I see that it's not actually going up the same amount. Here, we went up 5 squares, but then we went up 7 squares. For it to be linear, we need that constant addition. I would need to see that we went up by 5 and then up by 5 again. But since I don't see that, it's not linear. I could say it's not linear because we're not adding the same amount of squares each time we go up a step number. So then let's start to figure out what type of pattern this is. Looking at this pattern, we had talked earlier, for example, about step 100. And we said step 100, I can draw it correctly this time, was 100 by 102. To help us think about what this pattern is, let's make the jump to step n. Do you have any idea what step n would look like? Well, we had mentioned earlier there's this connection between the step number and the width. The step number and the width. Step number and the width. And so for step n, again, I don't know the numbers. I do know it's going to be a rectangle though. And I know that the step number tells me the width. So I know that would be an n. For the height, how are we getting to the height each time? How did we get that 102? Well, remember, we said the 102 or the 5, the 4, the 3 here. It was just whatever the step number is plus 2. It's whatever the step number is plus 2. It's whatever the step number is plus 2. So for step n, it's whatever the step number is plus 2. My height then would be n plus 2. So how does this help me when it comes to writing an equation to represent this pattern? Coming down here, we've got to represent the number of squares after n steps. Diego and Jada wrote different equations. Diego wrote the equation f of n equals n times n plus 2. And Jada wrote the equation f of n equals n squared plus 2n. Are either of them correct? Go ahead, make sure you are pausing the video for this one and spend some time looking at both of those equations and see if you agree with one of them, both of them, neither of them, and then come back to check and see how you did. To help us decide first if Diego's right, I want to come back up here and think about how we were calculating how many total squares were in each of these. Earlier, we had said step 1 had 3, step 2 had 8, step 3 had 15. If I asked you how many total squares were in step 100, how would you do that? Well, for me, when I was finding these earlier ones, I was going back to what we did in the warm-up, which was area. I was taking 3 times 5 to get to my 15. So if you asked me how many were in step 100, I would be doing 100, my width, times 102, my height. And so when we get to step n, if I do that same math, it's going to say I'm multiplying step n times n plus 2. And I have to use those parentheses there to make sure I'm multiplying everything. I'm taking n times everything. And so if we compare what I just wrote in red to what Diego's equation says, we agree with this first equation. It's just calculating area of a rectangle. For step n, one way you could find those total steps is by doing n times n plus 2. And that would give you the area of the rectangle, which is also how many squares there are. Looking at Jada's, she's got n squared plus 2n. And this, in the past with my in-person students, has been harder to figure out. Some people say, I don't know if it's right or not, but I know how to check. We said it earlier, right? You could check this equation by taking some of the numbers we know. For example, we know step 3 has 15, and we know step 2 has 8. And you might notice that if you put step 3 into this equation, it gives you 9 plus 6, it gives you 15, which is what we want it to give us. And if you put the number 2 into this equation, It gives you 4 plus 4. It gives you 8, which is what we want. So I've literally had students say, like, I have no clue where that equation came from, but I checked with numbers and it works, so I guess it must be okay, which is a great strategy. Absolutely. I want to take it further, though, and talk about where it actually came from. And some students don't connect it to the picture, but they connect it to this first equation. Once we know this first equation is right, look at that n times m plus 2. What could you do with this? We haven't seen it a lot yet with a variable being in front of the parentheses. We've seen it a lot before now with numbers, but you could simplify this by distributing. You could do n times n and n times 2 there. And if you do that, n times n we've seen before, and we've said that's the same thing as n squared, and n times 2 is 2n. And so if we said this is a correct equation, it means this one here is equivalent. It says the same thing. And so that one also would be a correct equation to write. The final thing I want to do, though, we connected it to this first equation. I want to go back and connect it to the pictures. And so if we look at that equation, we have said in all the patterns we've looked at before now that when you see an n squared, it means it's talking about there's an expanding square. And when we looked at these, I did what most of my students in class have done and said, like, there's no squares, it's rectangles. And I don't see a square here. But there is a way to find a square each time. Step 1, it would be us looking for a 1 by 1 square. Well, here's a 1 by 1 square. Step 2, it would be us looking for a 2 by 2 square. Here's a 2 by 2 square. Step 3, it would be us looking for a 3 by 3 square. Here's a 3 by 3 square. And so every single time there is a square, it's just part of a rectangle. Well, what is the 2n then? Well, for step 1, it would be 2 rows of 1. So here's 1, here's 1. So 2n is 1 and 1. 2n for step 2, it would be 2 rows of 2. So here's 2, here's 2. For step 3, it would be 2 rows of 3 because n is 3. Here's 1, here's 2. And so when we get to step n then, what we're seeing is there's going to be an n by n square. Let me get rid of the n and the n plus 2. There's going to be an n by n square. And then there's going to be one row that's n long and another row that's n long. And from that, we get our n squared, that's the part in yellow, plus the 2n. Below, I do have a better picture of this here, just where it's separated out. And I think that helps see it a little better. The purpose of this is this idea that when you are looking at these quadratic patterns, there are multiple ways you can see it. You can see the n squared we've talked about a lot. So for example, this would be a quadratic function, but sometimes the n squared is hiding. And instead of saying n squared, you can see somewhere in the equation that n times n piece. Both of these represent the same pattern. They represent the same function. One of them is just written as a multiplication problem, and one has already been distributed. It's been multiplied out so that you can see that n squared there. So the cool down for this lesson, and a great chance for you to practice and see how well you've learned the goal for this lesson, is on the screen here. Go ahead, pause this video one last time and try this problem to check in and see how you're doing. All right, hopefully you tried this problem here. So you're looking at the pattern. We notice for step 1, a 1 by 1 square, step 2, a 2 by 2 square, step 3, a 3 by square. So that right there is part of our quadratic pattern. We see that expanding square piece. For step 1, I see 1 extra square. For step 2, I see 2 extra squares. For step 3, I see 3 extra squares. And so as I continue this pattern, we notice that for each step number, I'm going to write it over here. For step n, I'm going to see an n by n square. That's how that step number connects to the yellow part of the picture. And then every single time I'm going to see a line of squares that is n long. So for example, step 4 would have a 4 by 4 square and then 4 extra squares there in purple. When we look at this then, is this relationship a quadratic function? Yes. I know it is because there's that n squared involved. Specifically, this pattern is the pattern n squared plus n. N squared represents that yellow part of the picture. I wish I'd written it in yellow. And then that plus n is that extra row of squares each time in purple. This is the last lesson where we're looking at these patterns with dots and squares. After this, we're going to make the change to stories, but understanding what makes something quadratic and how quadratic patterns grow is going to be helpful even as we start to look at real life situations. Hopefully you found this video helpful. Thanks so much for watching. See you in the next one.